This is part one of a simple introduction to CometBFT. Today, we're going to learn the very basics. What is a state machine? What is a replicated state machine? What are Byzantine faults and how do we handle them? And how does all of this fit into the CometBFT model? So first, what even is a state machine? So let's look at a simple state transition function. A state transition function is the definition of the state machine. It specifies exactly how the machine moves from one state to another. So given the initial state of the system S and a series of inputs to the system, here a number of transactions, here think more database transactions than financial transactions, those both get put into the state transition function F, which mutates the state, producing a modified state S prime and a series of outputs, so the result of each transaction execution. For Comet, the very initial state at the very start of the system we call a genesis state. And in CometBFT, that's stored in a genesis file. So we can't have non-determinism in that state transition function. So how do we get non-determinism? That can happen from network communication. Obviously can happen from any values that are included that get randomly generated. There may also be system architecture differences. So for example, if serialization depended on the endianness of the architecture or something like that, or floating point operations, those could introduce non-determinism. There may also be non-deterministic data structures accidentally used, introducing non-determinism. So for example, in Python, the hash map is non-deterministic, so the iteration order isn't the same across runs. And there's also parallelism, so we don't know how the scheduler is going to schedule various threads, so we may end up with race conditions. So as we will see, CometBFT will assume that your state transition is deterministic, so we have to be very careful when we're designing it and implementing it. So that's a state machine. What is a replicated state machine? So all it means is that you take a state machine that we just defined and you run it on multiple independent replicas. So every replica starts from the same initial state, executes the same ordered sequence of inputs, and uses the same deterministic state transition function such that all replicas end up in the same state, if they're behaving, which we'll get to. So why do people even do this? So some applications are replicated state machines are high availability, strong consistency applications. So the fact that there are multiple replicas gives us high availability, and the fact that the replicas end up in the same state provides strong consistency. So any application where people want those two properties, you'll find replicated state machines used. So anything where correctness and agreement are critical, so payments are a natural fit, but so are naming systems like ENS, the Ethereum name system. You can imagine supply chain ledgers, other asset registries, really any application where different parties need to rely on a shared tamper-evident state. Also, any application where you want a strong guarantee about the ability to participate in the system, so censorship resistance is another great application. So one replica in our system does not have the power to arbitrarily decide, I'm not going to include transaction 0. I don't like who sent transaction 0. And as an aside, the blockchain term fits in because when you collect together a chunk of transactions, we're going to collect them together into a block. So that's the sort of atomic unit of the blockchain. So either all the transactions are applied or none of them are. So the other piece is handling Byzantine faults. So Byzantine faults can be non-malicious or malicious. So people typically talk about the malicious behavior, but you could imagine a non-Byzantine non-malicious Byzantine fault being due to a bug in the software on one of the participants, and maybe the participant sends conflicting messages. A malicious fault might be someone who signs two different blocks. That's called equivocation. So replicated state machines handle these Byzantine faults by requiring agreement, i.e. consensus, on the ordered sequence of transactions. So each replica executes all transactions deterministically, starting from the same initial state and in the same order, ensuring that they all compute the same next state. So in CometBFT, if less than 1/3 of the participants, the validators, are faulty, then the system is able to make progress. So we basically ignore folks that are doing Byzantine faults. So there's two separate concerns, execution and consensus. So first, defining what a validator is. So in CometBFT, a validator is a node that's been assigned some voting power. So they're responsible for proposing blocks and voting in the consensus protocol on whether they want to accept blocks. And validators are the ones who are collectively deciding the canonical order of transactions. So, for example, you might have a network of 4 validators. Each validator maintains its own copy of the state machine. So, in effect, you have 4 independent replicas all running the same deterministic application and participating in consensus. So with that in mind, CometBFT separates two concerns. So there's the consensus part. So that's the fact that all the validators are going to agree on a single global ordering of transactions. And for Comet, the consensus engine is just taking in arbitrary transaction bytes. It doesn't even know what they are. It's ordering them into blocks and finalizing them using this BFT tolerant voting mechanism. Validators don't need to understand what the transactions do, only that they're properly ordered. And then the execution part, so the execution engine takes that ordered list of transactions and deterministically applies them to the previous state of the system. So given the same initial state and the same ordered transactions, every replica computes the same next state. So in Ethereum land, they call these the consensus layer and the execution layer. And this separation is one of the things that makes CometBFT so powerful as a tool. So the consensus part is handled by the CometBFT application, and the execution engine you write. So that's your state machine application. So the consensus engine only cares about ordering and finality, doesn't care about what the transactions actually are, whereas your state machine application defines the rules of the state machine. What's a valid transaction? How do the transactions get applied to the state of the system? How are we going to store the state of the system? So the two applications, CometBFT and your execution engine, talk to each other over an interface called ABCI. So that's what we're going to discuss in the next video, Application Blockchain Interface. Today we discussed what a state machine is, what replicated state machines are, Byzantine fault tolerance, and the general CometBFT approach. I hope this was useful, and thank you for watching.